In this video, we're going to look at something called colligative properties. And a colligative property is a property of a solution where something changes, and the thing that changes only depends on how much stuff is in it. It doesn't really matter about the identity. So let's put that in other words. So here I have a beaker, and inside the beaker, let's say I have some water. Now, water under normal conditions, we know, has a boiling point of 100 degrees Celsius, and it has a melting point, or a freezing point is usually what it's referred to, of 0 degrees Celsius. It turns out both of these things change as you dissolve substances into them. And so as you start dissolving things, two things happen. One is, as we start putting stuff in, when this goes to freeze, all the stuff in solution gets in the way. So if regular water normally freezes at 0, salt water, anything with water with stuff dissolved in it, will not freeze at 0. You have to get it colder. So maybe it'll freeze at -5. And the idea is the more stuff that is in this solution, the lower and lower that freezing point's going to get. So -6, -7, whatever the case may be. This is why you put salt in your driveway in the winter, because that salt will prevent the water from freezing into ice. It makes it tougher. So unless it gets really cold, the salt in your driveway will keep the water from freezing. Likewise, what happens with boiling is normally to boil, water has to escape to become a gas. So if I have water, when enough energy is imparted to the particles, they escape and they go into the gas phase. But when you start having lots of salt particles in the water, these particles block. They prevent some of these water molecules from reaching the surface. It makes it harder. So the water molecules have to push a little bit more. Instead of boiling at 100, maybe they boil at 105 or 106. It all really depends on how much stuff is dissolved. So it turns out it doesn't matter what it is you're dissolving, it just matters how much. If you have 100 particles, it doesn't matter what substance it is. 100 particles of anything will have the same effect as 100 particles of something else. That's what makes it a colligative property. So these are the two big ones we're going to look at, boiling point and freezing point. And there are equations which measure how much the boiling point and freezing point change. And one equation is, so delta TB, that means the change in the boiling point, is going to equal a constant. This is something we look up. It changes based on the substance, times the molality of the substance. So the higher the molality, the more the change in the boiling point. Another thing that goes in this equation is something called the Van 't Hoff factor, I. The change in the freezing point is the same equation, delta TF equals I, except instead of KB, it's KF times molality. So let's just give an example. Let's say that I have 10 grams of NaCl, and I dissolve that into 300 grams of water. And I want to know what is the new boiling point. So what I first have to do is calculate the molality of this solution. So if I have 10 grams of salt, I say, okay, how many moles? So 1 mole of salt, NaCl, is 58.44 grams. And so 10 divided by 58.44 is 0.17 moles. And 300 grams of water, I'm just going to skip ahead here, is 0.3 kilograms. So the molality of the solution is 0.17 divided by 0.3, or about 0.57 molality. So that is the molality of the saltwater solution. Then what I do is I look up Kb for water. Kb for water, it turns out, is 0.52 Celsius degrees per molal. What that means is, for every molality of this concentration, the boiling point will increase by 0.52. So a 1 mole solution will go up by 0.52, a 2 molal will go up by 1.04, etc. And the last thing is this I factor, called the Van 't Hoff factor. This just accounts for the fact that some substances, when they dissolve, break into multiple parts. So for example, NaCl, when it dissolves, doesn't just become one particle. NaCl breaks into Na plus and Cl minus. So effectively, if you dissolve 0.57 molal of NaCl, you end up with twice as much dissolved substances. You end up with about 1.14 particles, because they're going to make Na plus and Cl minus. So you can account for that with this thing called I. So if NaCl breaks into 2 particles, we say I equals 2. So to find the new boiling point, we say the change in the boiling point is equal to 2, which is I, times Kb, 0.52 Celsius degrees per molal, times the molality of the NaCl, which is 0.57. And effectively, we're doubling it. That's where that 2 comes in. So I say 2 times 0.52 times 0.57, and I get 0.59. So that means that this solution, the boiling point will change by 0.59. Now, regular water, we know, boils at 100 degrees Celsius. That's with no salt in it. So when I dissolve this salt in it, it's going to go up by 0.59. So the new boiling point will be 100.59 degrees Celsius. Not a huge change, but a little bit of one. The same thing will happen on the other end with the freezing point. The Kf value for water is something you'll usually look up, is actually negative 1.86 Celsius degrees per molal. So the freezing point is a little more sensitive to things dissolved than the boiling point is, but you would do the exact same type of calculation to calculate the freezing point. So I would do 2 times the negative 1.86 times the 0.57 to find the change in the freezing point. Water usually freezes at 0, and I would subtract and find the difference. But that's just a summary of colligative properties, and certainly we can do some more practice with this with the quizzes and make sure that that all makes sense. But until next time, I am Derek Genova. Have a delightful day.